Now we could enter a little bit the structure of a satellite. I mean, we enter the space segment, we look to a satellite, and we see what is its configuration, what are the parts of the satellites. To do that, we focus our attention on a telecom satellite, one of the satellites that are orbiting exactly in the geostationary orbit that we discussed a little bit. And we take as an example Artemis, that was an experimental telecommunication satellite by the European Space Agency. It was built in Italy, and it was one of the examples of the space bus produced by the former Alenia Spazio, that is to say a space company based in the area of Rome. If we look to the image of Artemis, we see immediately the large reflector antennas that represents parts of the payload, that is the set of instrumentation, onboard instrumentation, that is capable of allowing the satellite to perform its mission as a telecom satellite. That is to say, receive and transmit signals that are related to some telecom applications like TV broadcasting. Also, you can see the structure of the satellite as a main box. Then from out of the main box that are the solar arrays being deployed, and at the level of geometry you see that those surfaces are quite large. They need to be large in order to capture as much energy as possible due to solar cells, and they are oriented, the surface of those solar panels, they are oriented in order to capture at the most all the solar rays that are coming from the sun. The structure of Artemis is the classical structure, the classical configuration of a three-axis stabilized satellite, meaning that the satellite should, of course, point the Earth for its antennas, point the sun in terms of the solar arrays, so its attitude should be really kept under control. First, we have seen the pictorial image of Artemis. Now we enter a little bit the technical details of the satellite. Here we see the overall picture. We see very clearly the antennas for the L-band and the S-band antennas, with also the feeder of the payload. Then you see the solar arrays, you see the main box, you see other equipments like an optical data relay system that is relevant to the mission of Artemis. You see also on the top panel, that is the Earth-facing panel, also the TT&C antenna that connect the bus system to the ground station. Then we can sort of explode the picture and see all the components of the satellite. So you see here all the parts that are present in a satellite, and all these parts could be logically divided in subsystems. So the overall satellites, the overall spacecraft is made by the payload and the bus. The payload is what is all the equipment relevant to the application, the service that the satellite is supposed to provide, so the antennas and all the relevant equipment in order to perform its telecom mission. Then there is the bus. The bus is all the rest that allow the payload to perform the mission. And the bus is made of subsystems. So we first have a structural subsystem that supports all the other parts and the payload as well. Then we have a propulsion subsystem, because the satellites had some capability of propulsion in order to reach the final geostationary orbit, starting from the GTO orbit in which it is placed by the launcher. So the satellite is placed in an elliptical orbit by the launcher, and then there is an operation of circularization of the orbit due to the onboard propulsion by the satellite that is capable of producing some thrust to circularize the orbit and put the satellite in the final motion that is the one described before in terms of the geostationary capability. Then, as I mentioned before, there is the power subsystem made by solar panels, batteries, and all it is needed to provide to the payload and to the system of the satellites all the energy that is required. We will have the TT&C system, that is to say the telemetry, tracking, and command of the bus that relates the satellites to the ground segment that is controlling the status of the satellite and the mission itself. We have also a thermal subsystem that is controlling the temperature of all the system of the satellites, basically taking the heat from the parts of the satellite heated by solar arrays incoming to the spacecraft and bringing the heat in the colder part in order to be ejected by radiation in deep space. Keeping under control the temperature is a very, very important thing for our system. Then there is also the attitude and orbital control systems, control subsystem that is also named the avionics of our satellite, that enabled the satellite to provide the correct pointing and asset as a free body in space. He has to point correctly the station on ground and provide all the alignment that are needed to perform the mission. All those subsystems are also working with some data processing on board, so there is a data handling subsystem working as well. So all these hardware parts will not be working without the software that is keeping under control all the operations. So you might consider that a very important subsystem is also the data handling system of the bus. But all the parts of all the components of our satellites, in order to perform the mission, should have both an hardware and a software part working together. In this picture, we can see an image of the structural subsystem of Artemis with all the mechanical part. You see that there is a central cylindrical part inside which there are the tanks for the propulsion system and the combustion chamber and the nozzle of the system as well. Then this internal structure, that is the main supporting structure of the system, is related with some shear panel to the lateral panels, the north, south, east, west panels, on which all the subsystems are placed. There is a coverage on the top, that is the earth-facing panel, on which there are a lot of components for the payload. And you can see in the picture not only the description of the parts, but also the physical part of the central cylinder of the system. There are also alternative geometries for telecommunication satellites. In this case, this is TDRS, an alternative to Artemis, produced by an American company. The structure and the components of the satellites are the same, but they are organized in a different setting, meaning that for several reasons, for production, for industrial reason, for the heritage, the technological heritage of a company, the arrangement of the parts and the construction of the satellite might drive different geometry and different configuration for the satellite. But at the end, all the subsystem and payload component will be there. In fact, for each satellite, you can identify each and every part as being part of either the payload or a subsystem. In this case, we have a picture of a small Earth observation satellite, and out of this complexity, you can even use a color to perform this action. You can recognize each part as belonging to a special subsystem. So the logic of this complicated setting of hardware pieces is very simple, and all this complexity is reduced to a simple description in such a way that you know perfectly how the system is composed and which is the role and the functions of each and every part. You cannot talk about space systems without talking about the launch segment. Here I'm just providing a picture of the European launcher family as it is today. So we have the two configurations for Ariane 5. We have Soyuz that now is launched by Kourou base station, and we have the new small launcher Vega. This family will likely be increased by the development of a new launcher in Europe, that is to say Ariane 6. But this is the present configuration, and all those launchers are being launched from the Kourou base in French Guiana. Of course, there are many launching system capabilities from launchers from the US, from Russia, from China, India, and there are many nations now developing their own launcher and their own launch bases. We need to spend also a word on the ground segment. Of course, if the satellite is performing a lot of actions but is not capable of transforming any information to the ground, that will be useless. So the most important segment from the ground viewpoint is the one that is providing to the final user the real functionality that the satellite is offering. For instance, for us, the most important ground station for telecom satellites is the antenna that we have on the top of our house in order to enable us to receive the signal for our space TV. Of course, there are other kind of ground segments that are much more complicated with real big antennas capturing, for instance, the information of an Earth observation satellite. But there is also a capability on ground that should keep control on the mission. So while the ground segment that I just mentioned is working as the ground segment for the payload, you also need a ground segment for the bus. Since you need to know how the evolution, how the operations of the bus are evolving, and if you need to do some control or to issue some command to the satellite, you need to do that. So there is also a very important portion of ground segment that relates on the way that we track the satellite, we control it, and we have all the mission under control from the ground. So once again, the space segment, that is to say the spacecraft or the satellite that we have seen in detail, is just one segment. You need to have a launch segment to place it in the right orbit, to send it to space, and a ground segment to perform all the operations during the entire life of our spacecraft and the entire life of our space system. You might see here an important spaceport in Italy at Fucino, where Telespazio has a bunch of antennas that you might see. They are oriented in different directions to capture different satellites, and they are also, of course, able to move in order to capture the Earth observation satellites that are moving when passing on the base, and you have to track them and to keep alignment with them while the satellite is moving in the sky. I would like to conclude this talk talking a little bit about application and services. We have seen the reason why we go to space. We mentioned exploration, science, some commercial application in telecoms, but mostly let's say government-driven applications like Earth observations or like meteorological applications for weather forecasting. Now things are a little bit changing, and for instance, if we go to the news, we see that last year Google is buying Skybox. Skybox is a small spin-off company that is working to provide an entire new and really ambitious Earth observation program. The idea of this company is to be able in few years to deploy a constellation of satellites that will be able to take pictures of the entire Earth twice a day with a very strong level of detail resolution. And the idea of Google is that this kind of asset would provide a dramatic result in terms of business, in terms of new ventures, in terms of all applications that could be based on such a space asset. So there are not only government but also private companies that aim to enter the space business with a different pace with respect to the past. And another example is the example by the founder of SpaceX, Elon Musk, and this year is announcing the idea of building a huge constellation of microsatellites. We are talking about 4,000 of microsatellites. You imagine this number of satellites in order to provide satellite internet services that could reach billions of new users. So there is a real need because there are a lot of people worldwide, something like more than 4 billion people that lack internet access. So space systems, new space missions can provide a technological solution to withstand to this problem. And so this is another case in which private investors think that space asset could be really the way of providing new services and eventually create a new business and new economy based on space assets. In fact, we are witnessing today to a sort of revolution in the space field. So we have seen that there are new nations becoming space players like China or India, and now they are major players. China is able to send humans to space and has a huge program of application satellites. India is working on a lot of applications for citizens like distance learning or telemedicine that face really important problems that they have in their nations, that lack of terrestrial infrastructure. Then there is demand of new space activities coming from the market. And also we are experiencing the increase of cost for large aerospace corporation that is now not sustainable anymore, and there is a need for a reorganization of all the sector. So we can maybe think that in the next few years, such space system will have a new era. There will be a sort of new space versus old space. And in the new space of forthcoming years, space activity would be mostly pulled by demand of space services rather than pushed by technology. And the funding will not just come from governments, but from the needs of the market. Also, we might spin in the new space activity, new technology, maybe new technology from ICT, and we would have flexible launching technique to allow, for instance, huge number of satellites like the constellation proposed by SpaceX to be deployed. Also, the focus of attention would not be the focus of the performance of the spacecraft, but would be the performance of the service that we will be able to provide, and the big attention would be, especially for Earth observation, on the topic of the exploitation of data and big data, meaning a huge amount of information that should be managed somehow in a much better way than we are able right now. Also, new small satellite system might be developed, and such satellites should be high-tech, should have a launch technique that should be designed especially for them, and should perform precise missions. While today, SmallSat is just a low-cost item, basically launched as a piggyback, that is to say, a secondary system with respect to the main launch. So in the new space area, we should also think about new cost structure, a new organization of companies in order to have development cost at a much lower level than we have experiencing right now, and also the times for development should be much less. So we should have systems to be deployed in a much shorter time. So there is the idea that a new space industry might enter in the field, and the old industry should reorganize, reframe itself in order to be competitive with the new challenges for space. New space technology will be deployed. Of course, there will be enhanced payload technology, or we will see the advancement on onboard sensors, while experiencing a dramatic increase in the capability of data processing even on board. The technology of electric propulsion will take place, and larger onboard power will be needed to support such advanced capabilities both at the level of payload and bus. The satellite should be more autonomous in terms of navigation and guidance, and the telecom should also consider all the problem of encrypted telecom in order to have both the information and the command not being attacked from external bodies, and to have entire control on the system. We can also mention the idea of, in the next few years, there will be new infrastructure in space, new generation of navigation positioning system like GPS or Galileo, and there will be new Earth observation capability, the one maybe of Elon Musk with such a huge number of satellites, or systems of Earth observation, meaning the combination of all the capability of a system of existing Earth observation satellites combined together. We might have internet by satellites, and we might work on new inter-satellite links and networking. Us at La Sapienza, we are working on a project for a space infrastructure to provide almost real-time Earth observation services. The project is named EOS, Earth Observation Support System. Is being deployed by, has been studied by a group of students of the Master in Satellites of La Sapienza, and it was deepened by Gianluca Palermo with the help of Alessandro Golker of Skoltech. So we are proposing a low Earth orbit constellation as a data relay backbone intended to support client low Earth orbit satellites in data transfer and for TT&C, in order to overcome the problem of revising time and having a Earth observation mission that would work at almost real time. I would like to conclude my talk with this research proposed by my group and with a lot of trust and confidence on the capability of space systems of the future.